Okay, so today we're going to be taking a look at how to start and simulate a project for the PIC16F1619, which is one of the newest PIC16 chips on the market that has a new F1 core and core independent peripheral modules inside, which are really appealing. It's described in a book called This Is Not Rocket Science by Lucio Di Giazio. It's available from the Lulu shop for about $20. It's relatively inexpensive, and this author has done a number of really good books on the PIC. So what we're going to do for this example is we're going to take a look at how to initialize and run port A pin 0, which is a digital pin, to make it go logic high and logic low. So it's the sort of thing that we would do if, for instance, we had an LED, little light that needed to be connected to a resistor and then to ground like this, and we wanted to turn this light on and off, this LED going on and off. And we would do it by changing the voltage values of pin 19, which is port A pin 0 or bit 0. Okay, and it can actually be found on this side of the chip over here. So here's how we're going to do it. We're going to switch over to MPLAB X right here. And I'm going to start a new project like this, a standalone project. Next, I'm going to say PIC16F1619 like that. So I filtered for it. I hit next, next again. I want to simulate it, even though I could use some of these other debugger modules like the PIC4. I'm going to look for the compiler, XC8 version 2. I'm going to call this YouTube PIC16F1619 version 1. Okay. So I'm going to do something very similar to what I did for the PIC16F84 as well. Okay, so the project will come up here. Here we go. I right-click on source files. I say new, other, C, main file, next, default's good. I hit that finish button and we wait for it to set up. All right, next, I replace these two header files right here with include xc.h, which is that standard include file for all the PIC or microchip parts. I say return 0 right here, which is going to be the return statement for my main function. I need to set up the tri-state register for port A. So tris A is going to be equal to 0B. I'm going to put 8 digits in here for the binary number. 1, 2, 3, 4, 5, 6, 7, 8, like that. And all of them, since they're zeros, 0 for tri-state means an output. Okay, and so RA7 all the way down to RA0 are outputs. Okay, that means 0, like that. Okay, there's going to be that. Then port A is going to be 0, and we're going to leave all of the other bits. We're going to leave them as logic 0. And we're going to set RA0 to be a logic of 1. So RA7 to RA1 are 0 volts. RA0 is 5 volts. Then we're going to switch this over to port A is equal to 0B. We're going to turn all of them off like that. So RA7 to RA0 are 0 volts like that. Okay, so I don't see any warnings on the left side right here. I'm going to hit compile, that hammer right there, just to see what happens. Waiting to see what happens. There we go. Seems to be going. calling the XC compiler right there. And build successful. Great. Okay, so next thing we want to do is we want to set a breakpoint at the very first line of the main function, and we want to set up two views of the registers. So I go to Window, Debugging, and I want the I/O view like that. And unlike this PIC1684, there are a lot more I/Os. I'm looking for port A. I found it right there. Tris A is found right there, and port A is right there. Okay, and the other thing that I want is simulator I/O pin like that, and I can't do anything to it until the simulator is started. So I'm now going to hit debug like that. And I'm waiting to see that it is actually running the simulator and the debugger. It seems to have compiled it one more time. There we go. There we go. So it said it started running it. Now the user program has stopped. I take a look at here, and where the breakpoint is located, there's a little green arrow, which means that the program counter has stopped at that breakpoint. I can now go into the I/O pins subwindow right here and ask for, scroll down, RA0. Okay. It is currently in an analog input mode. That's how it started by default before we got to Tris A right here. All right. And next we want to switch over to I/O view right here. And we can see port A set up right here. And we can see Tris A set up right there. So we go and we step through, and let's see what happens to RA0. Okay, so what we see here is that it is currently in A-out or analog output mode. So it is not a digital output at all. Okay, next up, let's see what happens when we change the port A value and see what happens. This is going to be interesting. Okay. All right, we're going to go one more step right here. Look at that. It is at 5 volts. Okay, so it is acting as an analog output, but it set it to 5 volts. And now I'm going to do it again. I'm going to do the next step, and what value is going to be output here? Let's check this out. It's still 5 volts. Okay, so it didn't behave like we thought it would. However, what's interesting here is that the simulator and the debugging modes that we've got available to us are showing us some insight into its actual behavior, and the fact that I was wrong in assuming that everything was going to work out like it did on the PIC1684A. So now I have to go and reread the documentation to see what I did wrong in the first place. All right, so here you can see the value of using debugger and simulators in developing for your chip. In this case, the PIC16F1619. So in the previous part of the video, I made a mistake. I made an assumption that the PIC16F1619, this newer PIC, would behave similarly to the older PIC, the PIC16F84. And so I thought that the RA0 part of the register that connects to that particular pin that we want to use for digital output would behave the same way. And it turns out the simulator was showing us that it doesn't. So what it was showing us was that there was some analog feature associated with RA0 in addition to the digital part that I was hoping to do. And it was sort of blocking the behavior that I was trying to get out of port A. So we've seen, using the simulator, we've debugged, or we found a bug, and we're now in the process of debugging what that mistake is. How do we do that? Well, typically, since we've got that hint that we wouldn't have really seen otherwise, a printf statement in your microcontroller wouldn't have shown that at all. Really, we needed to be able to see into those registers to see that, and the simulator allowed us to do that. where do we go from there? Well, typically we go to the datasheet. The datasheet's a really good place to go. So I'm going to switch over to my web browser, and I've loaded up the page, the product page for the PIC16F1619, and you can see right over here that there is a Documents tab, and in the Documents tab there's a link to the datasheet. I load up the datasheet, and what do I see? I see all sorts of mumbo jumbo. I don't understand any of this. It's really busy and lots of little words that maybe I'm not familiar with. But I do know that I was looking for the tri-state register, TRIS-A. I was looking for port A, and I know that there's some analog thing that the simulator was telling me about. So I'll scroll for a couple of pages, and I'll see that, yeah, sure enough, it says intelligent analog peripherals. There's an analog to digital converter on this chip. And then if I scroll some more, let's see, we see that there's the chip layout, which doesn't really tell us that much of anything. I keep scrolling, and a table comes up. It's this pin allocation table for the different versions of the chip, this 14 and 16 pin version of the chip, and the 20 pin one, which is what I'm sort of hoping to use. And when I take a look at RA0 over on the left-hand side, right here, we can see that it does say that there is some analog component to it, both an analog input and, turns out, looks like a digital to analog converter, so it did an analog out as well, that's associated with RA0. So the data sheet is confirming what we saw in the simulator, that there is some analog feature to RA0 in addition to that digital component. So from there, what do we do? Well, typically you want to go and do a search for the keywords that you know. And in this case, I know about tri-state A or TRIS-A. So I'm going to do a Control F or Command F, and I go TRIS like that, A. And it shows me that it's part of different banks of memory, and I keep looking. And then section 12, port A registers, data register. Port A is a 6-bit wide bidirectional port. Setting TRIS A to 1 makes the port A pin an input. Okay, I knew that. And clearing it, setting it to 0, makes it an output, which is what we wanted. It also says the exception is RA3, which is input only. That's interesting. Don't need to know it right now, but we'll know it for later. Keep looking, oh, hold on, right here. Analog control. Ha! This is what we were looking at and what the simulator was hinting at. That there is a register called ANSEL A, or Analog Select A. Analog Select Port A. And the ANSEL bits default to the analog mode after reset. So it turns out that by default, as soon as the pin or the microcontroller turns on, that the pins associated with analog output or analog input are going to be analog, not digital. Luckily, there is some assembly code that's listed right here for telling us how to properly initialize port A. And so there's 3 pairs of commands to initialize this one, that one, and that one. So first it says to select the bank of memory that contains port A and to clear it. So this means setting it to 0B, 1, 2, 3, 4, 5, 6, 7, 8, a bunch of zeros. Same thing. Bank select A or latch A and clear it. So 0B, 0, 0, 0, 0, 0, 0, 0, 0, like that. Okay, and then what we need to do is we need to clear analog select as well. So set it to 0. So 8 zeros. And at this point, so port A, latch A, and cell A all set to 0. And then we can do what we need to do with the tri-state and then make the port voltages go up and down. Okay, so let's do that in code. Okay, so I'm going to erase what I had here first, like that. Okay, so I'm going to go, let me see, it said port A first. So we go port A is equal to 0B, 1, 2, 3, 4, 5, 6, 7, 8. Then it was latch A is equal to 0B 0000000, like that. And then it was, what was it after that? It was AND cell A. AND cell A is equal to 0B 1, 2, 3, 4, 5, 6, 7, 8, like that. And then we need to do tri-state. Yes. Tris A, we are going to set the tri-state, so the digital input or output state of the register to 0B, so binary, and we want RA0 to be an output. So we're actually going to make all of them outputs. 1, 2, 3, 4, 5, 6, 7, and 8. So RA7 all the way down to RA0 are all going to be outputs. And now port A, I can set it to, so I can set RA0 to be, let's start off as low. So 1, 2, 3, 4, 5, 6, 7, 8. So everything is going to be logic low. Then I'm going to make it logic high. Okay, so RA0. All right. This should work. So I'm going to compile. Make sure that it does compile. There we go. And let me see, I've got my I/O pins view, my I/O view, and now I'm going to hit debugger for simulation. There we go. All right, so we've hit the breakpoint right here. Port A is going to be cleared. Step, latch A we're going to clear. Analog select. So take a look at right in here. Is analog input going to change to be digital? Here we go. Step, done. So RA0 is now a digital input. But that's not all we need to do. We need to make it a digital output. So we do that with tri-state A. Switch it up, digital output. It's now a digital output. That's fabulous. And next we want to see that it goes a value of 0. It should contain a value of 0, and it did. It didn't change. Now the proof is in the pudding. Will it change to a value of 1 or logic high? And bingo, we got it. So now you can see that we have solved the issue of properly selecting digital output and changing the voltages or the logic values on those pins as digital outputs by using the simulator, by using debugging techniques, and by using that datasheet. All right, till next time.